Chapter 6, Neutralizing the Threat of Acid Rain, Part 1. In this lecture, we'll talk about the fundamental definitions of an acid and a base. We'll talk a little bit about what it means to neutralize an acid with a base, and we'll discuss the concept of pH, a fundamental measurement of the acidity or alkalinity of a solution. Neutralizing the threat of acid rain. Is normal rain acidic? When rain becomes acidified, is it worse in some parts of the country or not, and why? Can we stop this phenomenon of acid rain? This picture down below here looks like a Gothic gargoyle of some sort, spout. And you could see the face is fairly eroded away. There are many types of sculptures that are made of limestone. And limestone has a fair amount of calcium carbonate in it, which is a base. And when acid rain falls on those structures, it essentially neutralizes the base and erodes away the sculpture. So we'll go into the background behind that phenomenon. Please take a look at a video on acids and bases. So what is an acid? It comes from the Latin word acidus, meaning sharp or sour. Anything that you eat or taste that has a sour-like quality to it is most likely acidic. Wine is acidic. Orange juice, fruits have these have something called citric acid, the fruits and fruit juices. Wine has something called tartaric acid that comes from the grape. Acids conduct electricity because they form ions in solution. They're corrosive, so they can actually break down other substances. And there are a number of acids that react strongly with certain metals. We'll also talk a little bit about litmus paper. Litmus paper is used to determine if something is acidic or basic. There's universal litmus paper, which will turn a particular color depending on the degree of acidity. There's also just very simple red and blue litmus paper. If something turns the blue litmus paper red, then it's an acid. If something turns the red litmus paper blue, it's a base. So the fundamental definition of an acid is a substance that releases hydrogen ions in aqueous solution. The hydrogen ion has no electron. It is fundamentally just a proton. The hydrogen atom has one proton, so a naked hydrogen atom without its electron is often referred to as simply a proton instead of the hydrogen ion. Now, when we dissolve hydrogen chlorine gas in water, it dissociates completely into H plus and Cl minus. This is a bit of a simplification, however. Really, that H plus is so reactive that it interacts with other water molecules and forms the hydronium ion. So it attaches itself to another water molecule. Generally speaking, whenever we talk about acids and bases in solution, we're talking about in water. Frequently, we may write H plus, but understand that in solution, it's actually H3O plus. The Cl minus just kind of floats around, kind of interacts with water molecules, just slight attractions, but that's not too critical. It's the hydronium ion or the proton that is what makes a solution acidic. So this is what the actual reaction looks like, forming the hydronium ion. Now, what is a base? A base is something often referred to as alkaline. Alkaline has Arabic origins in the word. These are some bases in your home on the right. Drano, very strong, infamous base. Baking soda is a weak base. And of course, there's ammonia and other cleaning agents are often bases. What's missing from the picture are over-the-counter drugs you might find in a medicine cabinet. Many drugs are basic. They contain a nitrogen atom. And nitrogen, when it's attached to another organic molecule, has basic properties. Bleach is another base. And as you know, if you've ever touched bleach, your hands feel really slippery afterwards. Bases taste bitter. If you break open a ibuprofen or any other drug you have, chances are it tastes bitter. They're also corrosive. They also can conduct electricity like batteries, think alkaline batteries, but they don't react with metals like acids do. They will change pH paper. If you don't have universal pH paper, you pull out a piece of red litmus. If it turns blue, you have a base. But what defines a base? Well, it's any compound that produces hydroxide ions in solution. So sodium hydroxide clearly produces hydroxide ions in solution. For 1 formula unit of calcium hydroxide, we produce 2 equivalents of OH minus, our hydroxide basic ion. Just like the hydronium defined an acid, the OH minus defines a base. What about ammonia, NH3? I talked about that being a base earlier on, but it doesn't have an OH group in the compound or molecule formula. But when you add it to water, the nitrogen will steal a hydrogen from the water, leaving us with OH minus in solution. So the rule of thumb is if you have an alkali metal in group 1 or an alkaline metal in group 2, they will be bases. Additionally, compounds containing nitrogen also will act as bases, not as strong as the alkali metal bases that contain an OH minus, but still will have this basic property. When I refer to a strong versus weak acid or base, I'm referring to the degree of production of H3O plus or OH minus. For a strong acid, every molecule of acid you put into solution produces an H3O plus. For a strong base, every formula unit you put into solution produces OH minus, at least one. These are our strong acids and strong bases. There aren't very many of them. You may want to write down this list a couple of times just to keep it in the back of your mind, or this is something to put down on a note card, because if you're asked to determine whether an acid or base is strong or weak, you'd want to have this table in mind or be able to find this table. If it's not on this table of strong acids and bases, it's a weak acid or base. There are many, many weak acids and bases comparatively. There are only a few strong acids and a few strong bases. Let's take a look at an animation of a strong acid. In this animation, HX represents our strong acid. We will be adding it to the blue solution, which represents water, and we won't be showing the water molecules for clarity. So initially, you put the acid into water, and immediately
the acid begins to dissociate. Some people use the word ionize, but I prefer the word dissociate. Since it's a strong acid, it dissociates completely into H plus and X minus, the H plus immediately forming the hydronium ion with water.
Now, weak acid, conversely, is a substance that only dissociates a little bit. Only a few of the protons separate from the molecule to form hydronium ions, and the rest remain attached to the weak acid. An example is acetic acid. Acetic acid is found in vinegar. It's what gives vinegar its sour taste. Most vinegars are roughly 1 to 3% acetic acid. But acetic acid, only 4 out of 1,000 molecules will separate and form the hydronium ion, or in this case I have the abbreviated proton. The majority of the molecules will remain with the proton attached. So only very few dissociate to further form the hydronium ion. We use a double arrow frequently to indicate, okay, there's still a fair amount of products. Maybe a little bit separates, but most of it is in this form. A weak base is similar in that it also doesn't produce much OH minus. Ammonia is a weak base. Yes, it will form and steal some protons from the water molecules, but not many. Okay, the majority of ammonia, when it's in solution, when it's in an aqueous environment, is in the form of NH3. So you don't get as many OH minus ions forming. Let's take a look at an animation of a weak acid.
This animation uses HA to represent a weak acid. Again, the water molecules are left out for clarity. As soon as HA is immersed in water, it begins to dissociate. But as it's a weak acid, very little of it dissociates into the hydronium ion and the counter anion. So most of the acid is still in the undissociated form and has not contributed a significant number or as significant number of hydronium ions compared to the strong acid.
Thinker Buddy question. Which diagram best represents the composition of sodium hydroxide in solution? Water molecules are not shown. The sodium ion is represented by a little black circle, and OH minus ions are represented by a gray circle and a white circle connected. In picture A, there are 2 black circles separated, floating around, 2 gray circles separated, flowing around, and 2 white circles separated and floating around. In picture B, we have 3 chemical species, one with a black circle attached to a gray circle attached to a white circle, and another one with a black circle attached to a gray circle attached to a white circle. In picture C, we have 2 separate black circles, 2 gray circles attached to each other, and 2 white circles attached to each other. In picture D, we have 2 black circles separated and 2 gray circles connected to white circles as 2 separate chemical species. The correct answer is D. The Na separates from the OH minus, but the OH minus stays intact. It's a polyatomic ion. It's our hydroxide ion, and it never breaks apart. Thinker Buddy question. The difference between a weak acid and a strong acid is that a weak acid loses blank of its H plus ions, while a strong acid loses blank of its H plus ions. A weak acid loses all, and a strong acid loses some, A. B, a weak acid loses about half, and a strong acid loses none. C, a weak acid loses relatively few, and a strong acid loses all. D, a weak acid loses about half, and a strong acid loses all. Or E, a weak acid loses half, and a strong acid loses about 75%. The correct answer is C. The weak acid loses relatively few, while a strong acid loses all of its H plus ions. Thinker Buddy. A 0.1 molar HCl solution is tested for conductivity using the type of apparatus to the right. What do you predict will happen and why? The apparatus is a light bulb with two wires going into the solution being tested, and it's plugged into a wall outlet. The light bulb will blank. HCl is blank. The light bulb will A, not light up, not soluble in water. B, shine dimly, only partially ionizes in aqueous solution. C, shines brightly, completely ionized in aqueous solution. D, not light up. HCl is in molecular form in aqueous solution. The light bulb will shine brightly. HCl is completely ionized in aqueous solution. Ionized is frequently used in chemistry textbooks. I prefer the term dissociates, but either is somewhat valid. I think dissociate is a better term. But remember our conversation about electrolytes. Electrolytes are anything that forms ions in solution. So HCl is acting like an electrolyte. Now let's talk about acid-base neutralization. When acids and base react with each other, we call this a neutralization reaction. They will generally always form water upon neutralization and a salt, meaning a compound composed of the ions that did not react. An example of a strong acid and strong base reacting is hydrochloric acid and sodium hydroxide. They form water, and then the ions that do not react, the sodium and the chloride ion, are written side by side to balance the equation. In reality, if you recall, these are surrounded by water molecules. So this isn't entirely accurate, but we write it, again, to have a complete balanced equation. In neutralization reactions, we always form water. Now, this brings us to another topic called the ion product constant. Pure water dissociates to some extent, but very little. Again, in our previous chapter, we talked about whether or not pure water conducted electricity, and it didn't. The only reason why tap water may conduct is due to the ions in solution, either that came from groundwater runoff and it dissolved ionic compounds in the ground, or from metal ions in your pipe. But it does dissociate a tiny, tiny amount. And at room temperature, the product of the concentrations of the hydrogen proton, the acidic proton, and the hydroxide ion will always be the same. This is known as the equilibrium constant for water, or the ion product constant. This is a powerful tool because it means whenever we know the concentration of acidic protons in solution, we can always find the concentration of hydronium ion and vice versa. Let's do an example problem. Calculate the concentration of hydroxide ions if the concentration of hydronium ions is 1.0 times 10 to the minus 8. Well, we use our ion product constant, which says the product of the two concentrations is 1 times 10 to the minus 14, and all we have to do is rearrange to solve for OH minus. So we divide both sides by the concentration of H plus. So 1 times 10 to the minus 14 divided by 1.0 times 10 to the minus 8 gives us the hydroxide concentration, which turns out to be 1.0 times 10 to the minus 6. Thinker Buddy question. What equation represents a neutralization reaction? A. Nitric acid, HNO3, dissociating to form H plus and NO3 minus. B. Calcium hydroxide, CaOH parentheses 2 plus 2 HCl molecules goes to form calcium chloride, CaCl2, and 2 water molecules. C. SO2 gas plus H2O liquid gives us H2SO3, aqueous. D. Calcium 2 plus ion, aqueous, plus carbon dioxide gas plus water gives us 2 H plus ions plus CaCO3, calcium carbonate solid. B is correct. We have calcium hydroxide, a strong base with the OH hydroxide ions, part of the ionic formula. We have HCl, a strong acid, forming a salt, calcium chloride, and water. Now you can have a neutralization reaction with weak acids and weak bases. In this example, they just happen to be strong. Now let's talk about how we determine if a aqueous solution is acidic or basic in the lab. We talked about applying the solution to red litmus paper versus blue litmus paper, but typically we use a pH meter in the lab. The pH probe is an electrode of sorts that measures the conductivity of the solution. And pH itself is a measure of the concentration of H plus ions. It's the power of the hydrogen ions. We use a log-based scale to calculate pH. This helps us remove scientific notation from the equation and express the concentration of H plus ions in a more simple form. Now, if you were to try and calculate pH, all you would have to do is enter a negative sign and then your concentration of hydronium or H plus ions and press the log button. And that would give you the pH. To give you a feel of pH values for different substances around your house or in day-to-day life, you could see the pH of stomach acid is very, very low. That means it's very acidic. It's an inverse relationship in a way between the concentration of hydronium ions and the pH of a solution. The lower the pH, the greater the concentration of hydronium ions. Coca-Cola is actually fairly acidic. If you look in the ingredients, phosphoric acid is one of them. Oh, excuse me. And then you see pure water is a pH of 7. Blood is a little bit above that. Then you have ammonia, milk of magnesia, which is essentially milk of magnesia. Then you have ammonia, you have milk of magnesia. Milk of magnesia is magnesium hydroxide, which isn't quite a strong base, but it is a base. And of course, your things like oven cleaner and Drano are very, very basic. But it puts a nice simple number to our concentration of hydronium ions. Let's look at an example. For a solution with a hydronium ion or H plus ion concentration of 1.0 times 10 to the minus 3 molar, we should be able to punch that into our calculator, negative log, and the 1.0 times 10 to the minus 3, and it should spit out a value of 3. Typically, when we record pH units, we always include 2 digits after the decimal, mainly because most pH probes will produce data with 2 digits after the decimal. There are specific rules, but 90 to 95% of the time, this will be entirely accurate. One thing to note, when we use a log-based scale, it basically reduces our system by a power of 10. What that means is if you go from pH 3 to pH 4, even though it's one pH unit, you actually have 10 times as less hydronium ions at pH 4 than you did at pH 3. And this is just another example. A solution with pH 2 has 10 times more hydronium ions than a solution with pH of 3. So as far as declaring an aqueous solution as acidic or basic, we use the following rules. If the concentration of H plus equals OH minus, it's a neutral solution, like pure water. When you have more H plus than OH minus, we're talking about an acidic solution, and that would be pH less than 7. When you have H plus less than OH minus, so you have more OH minus than H plus, then we're talking about a basic solution, and the calculated pH would be greater than 7. Thinker buddy question. At any temperature, an aqueous solution is considered basic only if A, the H plus equals the OH minus concentration, B, the H plus is greater than the OH minus concentration, C, the H plus is less than the OH minus concentration, or D, the OH minus concentration equals 1.0 times 10 to the minus 7 molar. C is correct. The H plus concentration has to be less than that of the hydroxide concentration. This ends the first part of Chapter 6 lecture.